Mind closing the blind there for me, please and thank you. Loris, is that close enough to turn off the lights? Thank you, thank you, thank you. Perfect. All right, and I figured you would appreciate them being hole punched, so I didn't do the other folded booklet. Let's see how this goes. Okay. All right, let's open it up. Blank. What's that blank there for? I don't know. It just happened. So let's get started with some terminology before we do anything else. So we're going to do a lot of functions. So polynomials, then we're going to do exponential functions, and then we're going to do sinusoidal functions. So 3 units that have to do with functions. So they're very much related in the way we find stuff. The graph just looks different. Okay. So a polynomial function. Okay, do you want to contains only the operations of multiplication and either addition or subtraction. The textbook actually just says addition because you can add negatives, right? So I want you to know that it's also subtraction. Okay. Has real number coefficients. What are coefficients? Those are the numbers in front of your variables, right? So they can be real numbers. So I'm saying it could be decimal, fraction, root, you name it, right? Could be anything. Has whole number exponents, so the exponents have to be whole numbers, including 0, right? They have a degree, and this is where I'm going to start highlighting. The degree, and you probably recall this, even if you come from pre-calc, you will know this, right? The degree is determined by the greatest exponent of the function, okay? So you scan that function, and you see, oh, there's a 3, that's the highest exponent, then the degree of that thing is 3, okay? This is going to be big, guys. Leading coefficient, I call it LC, okay? The coefficient in front of the variable with the greatest exponent, right? So the coefficient that is in front of the greatest exponent, right? Think of that, is called the leading coefficient. Okay? The leading coefficient tells you what the end behavior of the resulting graph will be. Okay? Okay, LC tells you what the end behavior will be. Very important. So we're going to look at the leading coefficient. The word leading is misleading because you think of it's always the first thing that you see in the function. Not necessarily. It could be scrambled in the function. Just look for the highest exponent, and in front of that variable, that's where your leading coefficient is found. Okay, so I will probably scramble it on you a little bit. Most of the time it is the first number, 99% of the time. Constant. Every polynomial will have a constant. Okay, it is the number without a variable. Okay, so it's the number without a variable attached to it. The constant will be the y value of the y-intercept. So I just want you to know that the constant gives you, right? That constant gives you the y-intercept. I will do that more, like I will label it as I do some of the functions, so don't worry about it too much. Intercepts. We have the y-intercept and the x-intercept. The y-intercept is where the curve crosses the y-axis, and at that point x is equal to 0. So I want you to know that y-intercept, we always go 0, and then there'll be a number associated with that, right? X-intercepts is where the curve crosses the x-axis, and that's where y is equal to 0. So x-intercept is stated like that. Number other than 0, it could be 0 as well, but that you'll have to find. But we know that we have the 0 there in front for the y-intercept, 0 at the back for x-intercept. Degree of a function. We will explore and conclude that the degree of the function determines the shape of the graph. Okay, the degree of the function will tell us what are we expecting the shape to be. In grade 11 applied, we looked at linear and quadratic. Now we're going to look at cubic as well. So maybe I'll just do linear quadratic, and cubic. Those are basically our main types of functions that we're going to explore. Okay. All right. Let's do a little bit of an exercise right here to bring all of these terms together. Let me just adjust my camera here. Get that cursor away. Let me just focus one more time here. Okay, so here we go. So if this is your function, let's figure out the degree first. Let's do that first. I should have done that. The degree of this function, you look at, and it's actually 1, right? There's a 1 there. So the degree of this is 1. I will call this linear. Okay, if the degree is 1, we have a linear function. Let's look at the second one. Highest exponent is right here, right? So this has a degree of 2. You remember this from grade 11. What is that? A quadratic. Yes. All right. Next here, what is this? The highest exponent of the variable is 2. So this is 2. It's still a quadratic. And this one, if you look at the last one here, it has the highest exponent is 3. So this is has a degree of 3, and that's what we call a cubic. Right? Cubic inches, right, to the power of 3. So there you go. So that's what I wanted to do first and foremost. Now let's figure out the rest. For the first one here, the leading coefficient would be 2. Okay, the front of the highest power. The constant is not 5, it's negative 5. Okay. This is essentially the y-intercept. You want to write that down? That will be the y-intercept of this function essentially. So the y-intercept is 0, negative 5. I like to state it as coordinates, right? So we grab that straight from here and just plug it in there. Next, here, what's the leading coefficient? The highest power is x squared. It's actually negative 1/5, okay? You got to take the sign with you. The constant here is positive 25, because look at 25, right? It has a positive in front of it. And the y-intercept, therefore, would be that. Next, our leading coefficient. X squared is the highest power, so it's negative 5.78. The constant is negative 75, right? At the end there, no variable attached to it, so the y-intercept is therefore 0, negative 75. And then this one has a leading coefficient of 4.12. And what's the constant here? Negative 50, right? It's that number right there mixed in the middle. And so the y-intercept is 0, negative 50. So there you have it. Maybe what I'll do is, right, these are all connected. So right off the bat, you can tell what the y-intercept is just like that, just by looking at this. And the leading coefficient is going to tell us something else. We're going to look at the leading coefficient in more detail later on, but for now, I just wanted you to be able to extract it. And you're like, what about everything else? What about everything else in between, Mr. Dirksen? We don't worry about that too much, okay, for making predictions. Let's move on. So I had to, in order to compare them all on the same page, I had to go landscape on this, right? So I hope that is okay with you. So I'm going to add a lot of information here, so make sure you write this down, okay? First of all, let's look at the general form of every single graph, okay? They're all side by side. I can tell you that linear and constant are very much related, okay? But a constant function looks like this. Y is equal to A. It's just A is just a number, right? A linear function will look like this. Y is equal to ax plus b. And you're like, Mr. Dirks, I remember mx plus b, right? Do you remember that from grade 10? No, we now just look at a is like the leading coefficient here for us. We just stick with a, okay? It's rise over run. That's still all true, but we just stick with a. Okay? Quadratic, y is equal to ax squared plus bx plus c. Yikes. The c is hard to see there, but it's there. Okay. The cubic, I'm going to use a little bit more room underneath here. Cubic is y is equal to ax what? Cubed plus bx squared plus cx plus d. Wow, right? I will tell you this. When you look at a cubic function, everything can be 0 except for a, right? So all of these could be just not there, could be absent. As long as a is not equal to 0, that turns into a cubic, right? If you look at a quadratic function, these last two components, b and c, could be 0. As long as a is not equal to 0, you've got yourself a quadratic. So what the tail end is optional. It may not appear on your graph, right? Same with a linear, you need to have a does not equal to 0 there. Okay, so let's look at all these functions in terms of, let's fill this in here. Number of x-intercepts for one of these, and I'm going to grab a highlighter, and I'm just going to highlight those lines because it's hard to see, right? I'm going to highlight that. Just highlight the lines themselves. Okay. And so what this graph is supposed to, or what this chart is supposed to show you, is the general form of each polynomial function, right? You should recognize, oh, it's cubic. It's going to have one of these weird dips, right? Yeah. Zoom in on the equations. Yeah. Sure. How about I leave it like this, and you're just going to have to read what it says on the left there, right? Number of x-intercepts and stuff. So I'll just leave it like that. So at the top, you have the degrees and the resulting shape, right? Very important to know. And then we'll fill in the rest. Okay, so now number of x-intercepts. For this, the constant function, there are none, right? None except for, right? There's one unless y is equal to 0. Like if you're trying to graph the y is equal to 0, it runs right along the x-axis, in which case you have an unlimited number, an infinite number of x-intercepts. But you don't need to worry about that one too much. Number of y-intercepts, there's 1. And here's the end behavior. You read that, right? What's the end behavior? It tells you, like, you got to basically say, where does it start on the left and where does it go to in terms to the right? So from left to right, we would say from quadrant 2 to quadrant 1. So that's one option, like the top line there. Or if it's below, right, it would be from quadrant 3 to quadrant 4. That's what we talk about the end behavior. Where do the ends, right? Where do the ends end up? Do you remember domain and range? The domain and range, domain stands for x value. So for this particular function, every x value, so x is part of the real numbers, and we use squiggly brackets like that. that would be set notation. You could use interval notation that goes like this: negative infinity round brackets to positive infinity round brackets as well, because you cannot encompass, and we'll do more domain and range as we go. The range is just, you would go like this: y is equal to a, whatever a is, or you could just go square brackets and it's just literally just that number inside square brackets. That's how you would do the range, because it just stays there, right? It's just y equals a number. Can we do that maybe? What's the equation of this line right here? You just count, this is the origin right there, 1, 2, 3, 4, right? It's negative 4. So we can actually write that this one is y is equal to negative 4. Okay. And the top is 1, 2, 3, also 4. That one is y is equal to 4. It's just, y is always equal to 4, no matter where you go, okay? Make sure you write this down. Number of turning points, this one has 0, right? 0 turning points. It doesn't turn at all. It just stays straight. I can already tell you that. Let's go over to the linear. It also will have 0 turning points. Those two act exactly the same way. Okay, number of x-intercepts for the linear, it will always have 1, okay? 1 x-intercept. It will have 1 y-intercept. It will cross, right? What would the end behavior be? I will tell you this. If the leading coefficient is positive, do you remember which way the line goes? If A is positive, left or it's going to go up from left to right, okay? So this is when the leading coefficient is positive, and this is the leading coefficient being negative, okay? When the leading coefficient is negative, a linear goes down. If it's positive, it goes up. So we're going to have two different end behaviors here as well, okay? If the leading coefficient is positive, you go from quadrant 3 to quadrant 1, okay, diagonally across like that. If it's negative, you're going to go from quadrant 2 to quadrant 4. Okay, now it's going to get more interesting here. The domain is still the same. If you look at it spans, like if you're looking at the domain, right, the x values, this keeps on spanning indefinitely, so it's all real numbers. So all real numbers. So we use the squiggly brackets for set notation, and it's still negative infinity to positive infinity. It's going to be the case for all of them until we reach word problems, all right, guys? Once we reach word problems, no, the infinities are going to kind of dwindle, okay? The range is still also the same. The range is all of them because it keeps on going, right, up to the positive y values and down to the negative y values indefinitely. Okay? Let's look at the quadratic, the degree 2. Do you remember when the leading coefficient is positive, so put LC here, LC is positive, it points up. This one up here is also LC positive. The leading coefficient tells me that. And this will have a leading coefficient that is negative. That way I know it's pointing down. Right? So number of x-intercepts, you remember this one from grade 11? How many x-intercepts could a parabola have? This one right here, will it ever cross the x-axis? This one? No, so 0. This one touches it just right there once. So you could have 0, 1, or how many times does this one cross? 2. So to see how it gets a bit more interesting there, right? Could have 0, 1, or 2. Okay. Number of y-intercepts, 1. It does cross. You're like, well, Mr. Durson, this one doesn't, right? But it keeps on opening to the left indefinitely. It will cross it at one point. Okay. All of these, at some point, they open up indefinitely, they cross. So there's always going to be 1. End behavior. Well, let's consider LC positive, LC negative. If it's positive, what do you think it's going to be? The ends. This one would go from 2, right? It crosses like this. Where would it end up eventually? It would end up in quadrant 1. So quadrant 2 to quadrant 1. And if the leading coefficient is negative, it will end up in the 3rd quadrant at one point, and it goes to quadrant 4. I wouldn't mind if you flip these, like if you go 2 to like 1 to 2, it's okay with me, as long as you don't do that with the range. The range and domain order matters. Okay. Same here. The domain is still real numbers, so that's a little bit repetitive, but you could score marks easy if you just know what to write. Range is still this is different actually. The range is different. Here's where it gets interesting. If the LC is positive, it's going to be y, because it's pointing up, right? Y is going to be greater than the y value of the vertex. Say what? What is that? What is the vertex? Some of you know what the vertex is. I will label it on this graph in a bit. Just give me a second. Or it would be y to infinity like this. Yikes! It's gonna be cramped. I see it already. But if the LC is negative, it's y less than y of vertex. How am I going to do this? Negative infinity to y, like this. Square brackets, round brackets. Do you need me to zoom into that? Here, I'm zooming in. This is a y here. And we're going to practice this. So right now, just write things down. Just trust me, right? How many turning points? It actually has always one turning point. Always. And the last, the funnest one, I'm going to focus on the cubic. Oh, let's label our vertex. I'm going to use pink, right? There's a point where it turns, right? A parabola goes down, 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 and then there's a point where it turns. Or the other way, it goes up, 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 up until it turns, and the other way, right? So that part right there, if you want to go and highlight your vertex there, right? So you know the vertex is that turning point. Next, we have our cubic. Number of x-intercepts. That one has, it will always for sure cross at once, right? So it has 1, 2, or 3. Right? I wonder if the degree of the function has something to do with that, right? Degree of 1, degree of 2, there's a possibility to have up to 2. A degree of 3, there's a chance to have up to 3. So it does. There's our relationship. Y-intercept, there's just 1. Okay. And watch the leading coefficient tells me the end behavior. So if it's positive or negative, it has everything to do with it. Okay. Let's go up here to this. It follows the same pattern as a linear, right? So this would have an LC negative. This would have an LC that's negative, right? Because it's going down from left to right, it's going down. This one from left to right is going up, so LC positive. Okay. So LC positive, we can copy this. It's going to end up in quadrant 3 like this. If it extends, ends up in quadrant 3, and it goes to quadrant 1. Okay, I'm actually copying what it says there, right? And then here, if it's negative, it's going from quadrant 2, right, up here, and ultimately it's going to end up in quadrant 4. Why is that important to know? When you're graphing it on your calculator, if you can predict, oh yeah, this is coming from the left and it's going to go across and go down to the right, you can adjust your window and make it visible, or else you'll struggle. Okay. Domain is the same, all real numbers. The range is the same, it's all real numbers because it expands indefinitely. So the only one where you have to watch out is your parabola. How many turning points? 0 or 2. That's interesting, right? 0 or 2 turning points. This one has 0 turning points. It's just smooth transition, right? This one here would have 1 turning point and then 2, right? This one as well turns there and turns there, right? So 2 turning points here, none here. Okay, so it's either 0 or 2. That's what we're at with turning points. Okay. So I know your brain is probably exploding a little bit, but as we practice, I'm hoping that it will work out for you. Let me do this one more time. I want you to make sure you have this right. So this would be y is equal to a. This is y is equal to ax plus b. I don't know if you want to do the same. Like I find it's a bit crowded up there. And to be quite honest, I didn't go through the whole booklet before you're getting it because time was just too tight for me to get it back because they want at least 3 to 4 days ahead, right? And I'm making these as I go, basically. Sorry. There. Okay, there you have the 3 general forms. These are the general forms. And this is the A here is always our leading coefficient. Okay. I want you to notice this. What degree, the degree of this first one is 0, right? And the degree of the quadratic is 2. So degree of 0, degree of 2, degree of 1, degree of 3. Look at the end behavior. I'm gonna say this. Look at the end behavior between these two. It's the same. I don't know if you noticed that. So they both have an even power, even degree. So the degree of a function, right? If it's even, it will have the same end behavior. If the function is odd, it will also have the same end behavior. I just don't know what to highlight that orange. Orange does it, right? So I'm going to do this and this, this and this, right? Even, odd, odd. So, Mr. Dirksen, are you saying that if I came up with a quartic function. Do you want that quartic? No, we won't do it. We won't do it. But I might ask you, hey, if this isn't a polynomial with a degree of 8, what would you know? What would you know about the end behavior? You should be able to tell me it's going to be quadrant 2 to 1 or quadrant 3 to 4 if it's even. If it's odd, right? If it's odd, then the end behavior follows, right? So that is a pattern that they want you to know. The province wants you to know that the degree coincides, if it's odd or even, coincides with the end behavior of that function. Because we can't cover them all. We can't do quartic power of 8 because the graphs do look weird and different. They do look different, but the end behavior is what we're talking about. All right, guys. Let's jump in and do a little bit of like graphing here. Use our calculator for this. I have Desmos ready here on my iPad. And why iPad? Because that way I can make it onto the I can make it appear on the video, right? But I have right now just a constant function here. Y is equal to A. So you should be able to know, right? As the value of A changes, the line, if it's a constant function, it just, right? It just tells you where is it going to cross the y-axis, right? So I think you got that part. Let's stop that slider there. If it's a linear, right? Let's make A slide again. As long as it's positive, it's going to be pointing up, and then it's negative, it goes down, right? The steepness is also affected because it's the slope, remember, rise over run. But just focus on the fact it's a little bit too fast, right? It's like a video game. Okay, anyways, stop. I guess not. My Apple Pencil is, right? So if it's positive, if A is positive, it's going to be going up, right? And if it's negative, it's going down. What happens if I change that constant? That's important to know as well. Come on, Apple Pencil. There you go. See, if you change that constant at the end, it shifts the whole, it changes the y-intercept for sure, but it actually changes every single point on that line. Okay, so that constant shifts it back and forth. So that's a linear. Let's turn that off. Let's do a quadratic. So if as long as A is negative, it's going to be pointing down, right? A is negative. As soon as A is positive, it's going to be pointing up, right? So negative. Why does it turn linear at one point? A is equal to 0, now it's a linear, right? So you can't have that for it to be quadratic. But again, look at the constant. In this case, my constant is C, right? So I'm going to turn that on and off and see what it does. It does the same thing as it has been doing. So the constant at the end shifts the whole thing up and down. Mr. Dixon, does it change the y-intercept? Yes. Does it change the vertex? Yes. Does it change every point on it? Yes, right? So that's what the constant does. It affects basically the height of it, right? And last but not least, you've got your, oh, did I want to talk about, yeah, I wanted to talk about the fact that the constant, well, like here, there's no x-intercepts. And then right there, oh, there's 1 there, 1, and then 2, right? So that's why there's possibilities there. The cubic, that's that one. So as long as A is positive, right, it will be pointing up like this. As soon as it's negative, it goes the other way. Okay, so that's what A does. That's what the leading coefficient tells us. What does B do? Well, watch. Whoa, right? It makes the turns just a bit more accentuated, right? It makes the dip on either side be a bit more accentuated, okay? So there you could have right now how many x-intercepts? There's 1 there and another 1 there. What does that constant do? Remember, the last number is always the constant. It will do the same thing as before. It will just shift everything up and down. 1 intercept, 2, 3, 1, 2, 3, right? Like it changes. So the D value changes the height of it again. So the, watch, it's 5.92 right now. If I were to tap on that, that's your y-intercept right there, right? It matches. You're falling asleep because you're on your screen all the time, so you're so used to it. Screen, that's when I fall asleep, right? Anyways, let's keep going. Match each graph with the correct polynomial function. I think this is asking for a lot. I think I'm diving right in here. So I will guide you a little bit. Let's go find our linears first. So this has a degree of 1. Degree of 1. Where's another degree of 1? There's a degree of 1 here. Let's figure those out. Which graphs would be potential candidates for that one? These two, right? These are linear. You should recognize that. They both have a -3 y-intercept. You notice that? Both of these have a -3 y-intercept. Let's label that here. This is 0, -3. And this is also 0, -3. So that's not helping us at all. Okay. Which one would you pick between, like for h of x -1/2? Which one would you pick between these two? You can do a few things here. If you just plug in a value, for example, this one right here is negative. This is -1.5, right? But I would say this: if a is smaller, right, it's flatter. It is flatter, right? So this one we would have to say this is h of x -1/2 x minus 3. I usually wouldn't do that to you. I wouldn't have both of them with a y-intercept of -3. I would make one -4, -5, right? A larger is steeper. So this one would be q of x. Have you ever had an equation called q of x? Well, today is the first time, right? So we're done with that. We've checked those off. Okay. Let's look at our quadratics here. We've got a quadratic here. This has a degree of 2, and this has a degree of 2, right? These are both quadratic functions. That is more like it. That's more appropriate for our situation here. Let's look at this first one. Let's focus on which way is it pointing, right? It's pointing up because there's a positive there. This one is also pointing up because the leading coefficient is positive. Okay. So we know both of them are pointing up, but one of them has a -2 y-intercept and the other one has a +1. So that's how you can narrow it down, no problem, right? So let's go ahead and find this one. This one has a +1 right there. Okay, you want to go like this, 0, 1. Therefore, this one gets the k of x. X squared minus 2x plus 1. This one gets that one because of this. We know that it matches there. Okay, that's the giveaway for this one. I will also do this. Leading coefficient is positive, so it's going to be pointing up like this. And then the other one obviously needs to be this one, right? The j of x. Okay, this is, I'm going to make a point here, bring it out because it's too crowded there. 0, -2, right? Therefore, j of x is going to be x squared minus 2x minus 2. There is the giveaway. The giveaway is the y-intercept. And it's quadratic. The leading coefficient is positive, so we're pointing up, which is what's happening there, right? Sorry about that. You can't see that. That leaves us with two cubic functions. Two cubic functions, which is the two here. Let's look at the graph and then get the equation. You ready? What's the leading coefficient for this one? Just by looking at the graph. It's going up from left to right. Okay? It's positive because it's going up from left to right. This one, the leading coefficient would have to be negative because you're going down from left to right. So I'm not looking at the equations right now, I'm just looking at the graph, right? Leading coefficient positive, leading coefficient negative, just by looking at the end behavior, okay? So I need a leading coefficient of positive. What's the y-intercept for both of them? Let's figure out the y-intercept. What is it for this? It's 0, -2. And for this one, it's 0, -2 as well. So that doesn't really help us to narrow it down. So we're going to have to go by the leading coefficient. So we go up here and pick the one that has a leading coefficient positive, right? So you look at both of them. This one is positive. So we're going to copy that one down for the one that's has a leading coefficient that's positive. So we're going to go px is x cubed minus 2x squared minus x minus 2. Whereas the other one is g of x is negative x cubed plus 4x squared minus 2x minus 2. Okay. So maybe perhaps the better idea is to go through your graphs, look at the graph and be like, what's the leading coefficient supposed to be here? What's the y-intercept? What's the leading coefficient? What's the y-intercept, right? That's how you narrow it down, and then you go pick your equation. Okay? You're going to have more of these. I have more, so you can practice that. Okay. Let's get on to the next page here. This is what I just talked about before. Okay. I'm just going to narrow it down. It says here, linear and cubic, right, have similar end behavior. Quadratic polynomials have, they call it unique because if you don't consider the constant, then it would just be unique, but similar to constant. You can write that down. Similar to constant functions. So even exponents, odd exponents, odd degree, sorry. Let's go degree, not exponent. The exponent obviously would be, but we're talking about the degree. if you had a degree of 4, you don't have to write this down necessarily, but the graph, depending on various things, but it kind of looks like this. It's like a W. It can obviously vary, but it has the same end behavior. So if this would be a leading coefficient that's positive, if you had a leading coefficient that's negative, it would look like this. So the end behavior is still the same as a quadratic because it's even, right? It has an even degree. This is a quartic. You don't need to, you will not have to deal with it in terms of finding points on it or graphing it. You don't have to worry about it, but you do need to know that even powers, even degrees have the same end behavior, odd degrees have the same end behavior. Okay? A lot of information, I know. I'm going to try to synthesize that in a bit. Okay, now is where we're going to talk about how to graph these things on the calculator first, and then on paper. When you're given an equation, enter it into y1, press y equals to access the equations on your calculator. Okay, so most of you know that, you remember that from previous years. So if you grab your calculator, you go y equals, you might already have stuff in there. I would press clear right now. Just go clear, arrow down, clear. Even if one of these plots is turned on, go to it and hit enter. Make sure it's not highlighted. So right now, for example, if yours looks like that, just go up and hit enter. You don't want that to be, because it's going to conflict with what we're doing here. You're going to get an error quite often if that's turned on. Okay, we use it later. So that's where you put in your equations. Next thing is your window settings. The window settings essentially set the dimensions for the x and y axis that will be displayed on the screen, right? Pressing window allows you to adjust the window to make sure you're able to see all the intercepts. You need to see the intercepts, local minimums as well as local maximums. You're like, what? Just hold on for a bit. Watch this. This is very important. Only change x-min, x-max, y-min, y-max. Okay? Other teachers might change the scale and stuff like that. I don't do that. It's not necessary. So sometimes you'll be graphing and you will only see part of it. You'll be like, oh, this looks interesting, but you need to see more. Okay, so if you see something like this, it's clearly telling you need to increase your x max for sure. So if you do the change, you should then possibly see something like this. Okay, so changing your window allows you to see everything. Zoom. I use Zoom, but not as much, but maybe I'm kind of being flexible and I want to introduce that to you. Pressing Zoom allows you to quickly change your window. So Zoom standard, that's one of the options, changes all 4 entries to -1010, -1010. And you're like, what is that, right? I mean this. The first number is x-min, the second number is x-max. Y-min, y-max. So if I ever ask you for your window entry, if you see 4 numbers consecutive like that, it's basically just telling you what these values are. Okay? So let's do an experiment here. Grab your calculator. Press graph. Just press graph. I don't know what you're going to see. I honestly have no idea. You might actually have something in there. Doesn't matter. Zoom. So this is your window right now. If you go press window, press the window button right up here. There they are. X-min, X-max, skip. Then there's Y-min, Y-max. These are the only 4 parameters that we're going to change here. If you press zoom and then zoom standard, zoom standard, let's all press that one. That's the 6th option. That's one that I use quite often. it will change your window to a standard window, which goes negative 10, 10, negative 10, 10. Okay, so if you go to your window again, you will see that those entries have been changed to those parameters. So zoom standard kind of resets your window. Okay, use this to reset the window. Okay, zoom stat will be used when performing regressions. We'll do that later. And then there's zoom fit. It will be helpful to at least get you started. You most likely have to make changes after. Where is zoom fit and zoom stat? You guessed it. Press zoom. Zoom stat is way there, option 9. Zoom fit is right after it, so you can press either 9 or 0 to access that. Okay. I'm going a little faster because this is technically has been covered in grade 11. So if you're struggling, I can help you out with that. Okay. When you graph a function on the calculator, you can extract points from the graph by using calculate functions. Press second trace, right? You will use the calculate function of the calculator by pressing second trace. And if you've been in grade 11, you know exactly what I'm talking about, hopefully. Okay. So let's press that all together. Press second and then trace, which is actually accessing calculate, right? That option there in blue. And these are the functions you can use to extract information from the graph. I'm only going to use value, minimum, maximum, intersect. These are the, I don't really use the 0, okay? And 6 and 7 never being used in this course. Okay? That is like university or calculus stuff, right? So we only use 1, 3, 4, and 5, okay? So I will use this one, this one, this one, and this one. 0, if you really want to know how to use it, I will not be using that method, okay? But what do they do? Value determines the y value if you're given an x value. Minimum, it's used to find a low point, a dip on the graph. The maximum is to find the high point or the peak on the graph. Intersect will be used to determine the point of intersection between two lines. Okay, and so that's what we use it for. So let's graph one, shall we? So let's enter that. I start nice and easy with a linear. So everybody with me, y equals. How do you enter that coefficient? I do this in a sense in my calculator. I put brackets around it. So I go bracket, and if you're new to this course, when you're entering a leading coefficient, you got to use negative down here, not minus, because it's going to give you an error if you use minus, okay? So negative 2 divided by 3, close brackets. This is your X button right here, everybody. I'm hovering on it. That's your X variable. Don't use times. It's going to be wrong. X variable right there, plus 15. Okay? And then we're going to hit graph. So type that in, then hit graph. Oh, you see a little speck up there, right? Well, I want you to know this. The leading coefficient is negative. You should recognize that that means that this line is going to go like this. Right? Leading coefficient is negative. This is what's going to happen. What's the y-intercept here? 15 positive, right? 0, 15. So the exercise you were just doing is to help you out determining your window. You know, when we press zoom standard, the highest y value we see is 10. So we need to change that. Go press window, go to your y max and change it to, I don't know, I'm going to go 40. It's not set in stone, whatever works for you, right? And then hit graph. It's going to reset it. So now we see the y-intercept. That's perfect. We still want to see the x-intercept. So you go back to window, and I'm going to change my x max to 40 perhaps, 20, whatever works for you. And now we see the important points. We want the x-intercept, we want the y-intercept to be visible. So I'm going to do this on here. Window, write this down so you have that. I'm going to tell you what I've used to see this. Okay. That is what I've done here. So in this case, we have no maximums or minimums, but we do have intercepts. So this is what I'm going to do on the side here. X-intercept. This is how I find the x-intercept. Watch carefully. I let y2 equal 0, and then I go second, trace, intercept. Does that ring a bell, guys? Maybe, maybe not. So I'm going to go to y2. Where is that? I have to press y equals. I'm going to make the second equation equal to 0. That's essentially a constant function, right? And then I'm going to hit graph. And when you hit graph, you see that line on the x-axis, right? I want to find that point of intersection between this graph and the line that I'm interested in, because that's the x-intercept. So that's where the second, trace, intersect. Did I say intercept? It's supposed to say intersect. My bad. Enter, enter, enter. You just keep hitting enter until it actually calculates what it is. And the answer is 22.50. You are allowed to do this manually, algebraically, like you learned in maybe IAPR or pre-cal, but it's not going to be fast enough for most of the things we're doing. The y-intercept, I will show you how to find the y-intercept using your calculator, even though we know it's 15. Even though we know it's 15. We just go second, trace, value, and then we let x equal to 0. So second, trace, value is the first option. Let x equal to 0, and voila, there it is. 0, 15. With a linear, that's all you need to graph. That's all you need, okay? So watch carefully here how to graph, how to be successful in this course when it comes to graphing. When it's a non-contextual scenario, we're using all 4 quadrants, okay? No context, okay? I will make that very clear. We're graphing now without a context. We don't know what x is. It's not time. There's no money, nothing, no variables. So we just call this x-axis, y-axis. And then you need to come up with a scale. You need to come up with a scale. It doesn't have to be the same as mine as long as it's consistent. So we want to make sure we fit that y-intercept 0, 15, right? We want to make sure that works. I can tell that if I go up by 5s here, you need to make sure you clearly indicate where those markings are. That is a consistent scale there. Another one up would be 20, right? And then you do the same thing going into the negatives. You don't have to do every single one. Just go like this maybe. Just tell me a few going into the negatives. So that works with the y scale. It has to be consistent. You can't go 5, 15. You can't do that. You're going to lose a full mark. But the x-axis can have a different scale. That is okay. So 22.5, if I go 5, 10, 15, 20, then I'm going to run out of runway. So I'm going to go like this. 10, 20, 30. And I'm going to go into the negatives. Negative 10, negative 20, negative 30, like that. So you have a scale. You labeled your axes. And now just put the points down. 0, 15, 20, this would be, right here would be 25. So 22.5 would be right about there. Grab a ruler. Don't just hand, right? Like you need to have a nice straight line because the shape does matter. There it is. And you need to have your equation. Look at what I did up there. What is next to graph way up here? It says scale, labels, intercepts, min or max. We don't have min or max with something that doesn't turn. Okay? If it doesn't turn, there's no min or max. No min or max with graphs without turns. Okay, that's another entry there. Mr. Dixon, do I need to label the points right on here? No. As long as if you have them somewhere figured out on the side, as long as they match, you're good to go. Okay? You're good to go. I would like to do one more before we go, at least one more, like one with a dip. Okay? Once you do enough of these, everything that I talked about at the beginning that kind of right was a bit overwhelming will come together. You will start seeing a pattern. Okay. By the way, what we did here is these are the characteristics. Everything we did here are the characteristics of this particular function. Okay. And now you see why these booklets are so thick, because I give you so much room, right? There's this one page dedicated to this one graph, right? And I did that for a reason. So let's figure out this. This is what? The degree is 2. The leading coefficient is negative. The degree tells us the shape of it, correct? It could be this or that, right? Sorry, I know I'm fast forwarding because I do this all the time, right? But you should, down the road, degree of 2 parabola. That's the shape of that graph. That's what we call it. Leading coefficient is negative. So which one of these am I looking at? I'm actually specifically now looking at this. It's pointing down. Okay. And the y-intercept, let's figure that out right away. It's 85. You can go like this, y-intercept 85, but I prefer you stating it like this because it's actually a point. Okay. So that right there helps you when you graph it. So enter this with me into your calculator. That's the most important thing right now. Do you know how to type this in? So you go to your y equals. You clear the first one. I will leave y2 equal to 0 because there's a chance that you're going to need it anyways. So type that in exactly as is. Negative 0.067 x squared. You need to make sure you square it. Can I warn you? I warn you with this, guys. Sometimes when you type in the exponent squared, you need to go arrow sideways to come back down to the main floor. It somehow stays up there on your exponent, and that will get, like, it will just throw off your graph. You're like, Mr. Jackson, what's that negative 200 to 800 doing there? What is that? This is the domain I want you to consider, from negative 200x all the way to positive 800. And you're like, why are you doing that? Because I don't want you to have to graph the whole thing, right? I want you to kind of just narrow it down a little bit. But let's go ahead and try to graph this. Let's try to graph that. Oh, I saw part of it. And you can clearly tell this is going like this, right? So you know this is going to go up and down like that, correct? You kind of have to imagine it. I wish we could just do this, right? Like with our iPhones, to zoom out and in. That would be super nice. But what do we know? The y-intercept is 0.85. It's way up there, right? That helps you in part. So we're going to go to our window. I'm going to go to y max because that's the ceiling, right? I'm going to go not 85. I'm going to go what? 200? 150? Let's try it. Oh, it's still, I can see more. You see how your y-axis looks all weird? Don't worry about it. I'm going to go window. I'm going to go 500 for y max. Oop. Still not right. I'm pretending to not know what I'm doing. Okay, guys. Should I go 2000? Right? Like it looks like it's going to go up for a while. So I'm going to go all in here. Did I type it in right? I did. Okay. So what else do I need to do? Window. I'm still not seeing the ceiling, so I'm going to go 5,000 for the Y max. And now it's going this way, right? So what do you need to increase? The X max. Let's go 250 there. Oh. I'm going to go further to the side. I'm going to go 1,000 to the side. And I'm going to also increase this one to 10,000. Enough is enough, right? Oh, there we go. Finally, it worked. You want to look at my window? There. So I increased this to 1,000. I increased this to 10,000 because I just needed to keep expanding both maxes, right? Y max and X max until I started to see this. So I'm going to write this down for you. Window is optional. I will never really ask for it on a test, but here you have it. Okay. I'm going to make one more change. I would like to see a little bit below more below the x-axis. So I'm going to go like this, window, y min, I'm going to go negative 100. See, now you see a little bit below it, just a little bit. So that means that I need to change this to negative 100 here, the first entry. This does have a turn, okay? So I'm going to figure out the x-intercept. Is there more than one? Yeah, there's x-intercepts. Tell me your keystrokes. You're going to let y2 equal to 0, second, trace 5. So second trace 5. Watch this now. It doesn't matter which side you go, but it will find the closest one to where you are. So for example, right now the cursor is there. Which x-intercept is closer? This one, right? So if you hit enter, enter, enter 3 times until it says intersection, don't try to find it manually with arrows, okay? Don't do that. Just copy that number, and we have 721.120. Let's find the other one. I'm going to show you a trick here. Second trace 5. You know how you can go all the way over, but you can jump curves by going up and down arrows. So if I go up arrow, it jumps to the red, and then you can just, it's faster to go across to the other side. Now you're actually closer to that one. So if you press enter 3 times, it's going to give you that, and that's negative 1.760. So you've got that. Y-intercept, do we know it already? Yes, we do. So I'm not going to use my calculator for that one. But you have a turn. We call that max, right? There's a max there. In this case, there's a high point. There's that peak. So you guessed it. You need to, we call it the vertex for a parabola. And we're going to go second, trace, max. Don't use min if it is a max. It's still going to try to find it, but it's going to be the wrong answer. Okay. So watch how this works. Second, trace maximum. That's the fourth option. You can press 4 if you want, or just scroll down to it. And it's asking you for a left boundary. So basically it's saying, hey, find any point to the left of the vertex. You gotta know it's up there. Anywhere on the left is fine. So use your cursor sideways, don't go up and down, right? Hit enter, and then you go past it to the right because it's asking for a right boundary. Hit enter. So now you're telling the calculator somewhere between here and here. Every time it says guess on our calculators, you hit enter one more time. It's just asking you, do you want me to start? And then it's 359.68 and 8,752.73. We're not going to graph it today. It's not going to work out. What I want you to do is I want you to do the same thing. I want you to find, put this in your calculator, find all the dips, the turns, and the valleys, and the peaks, the intercepts, everything, so we can graph this together tomorrow. Okay? So this is your homework. There's a couple more, but I'm just gonna ask you to familiarize yourself using the calculator. This is gonna be leading coefficient is negative, right? It's gonna go down like this, except for this is a cubic, so it's probably gonna do something like this. This is for homework, finding the intercepts, turning points, and so forth, right? Thank you, guys. I almost lost my voice here.